Welcome to Chapter 13, Introduction to Optimization Modeling. Introduction. Spreadsheet optimization is one of the most powerful and flexible methods of quantitative analysis. Excuse me. One specific type of optimization, linear programming, is used in all types of organizations to solve a wide variety of problems. All optimization problems have several common elements. Decision variables, the variables whose value the decision maker is allowed to choose. Objective function, objective for short to be optimized, maximum or minimum. Constraints that must be satisfied physically, logically, and economically, restrictions depending on the nature of the problem. Excel uses its own terminology for optimization. Decision variable cells contain values that can be changed to optimize the objective. The objective cell contains a quantity to be minimized or maximized. The constraint imposed restrictions on the values in the decisions variable cells. Non-negative constraints imply that decision variables cells must contain non-negative numbers. Really? Steps in solving an optimization problem. Model development decides on the decision variables, that objectives, the constraints, and how everything fits together. Algebraic model derives correct algebraic expression. Spreadsheet models relate all variables with appropriate cell formulas. Optimized systematic choose the values of the decision variables that make the objective as large for maximization or small for minimization as possible and cause the constraints to be satisfied. Feasible solution is a solution that satisfies all constraints. The feasible region is a set of feasible solutions. An infeasible solution violates at least one constraint and is disallowed. The optimal solution is the feasible solution that optimizes the objective. Optimized step. Additional topics. Algorithms have been devised for searching through feasible regions to find the optimal solution. The simplex method is an algorithm used for linear models. Other more complex algorithms for use for types of models. Solver, add in with Excel, finds the best feasible solution for the appropriate algorithms. Sensitivity analysis follows up the optimization steps with what-if questions related to the input variables. Good software allows you to obtain answers to various what-if questions quickly and easily. A two-variable product mix is a product mix problem. A company must decide its product mix, how much of each of its potential products to produce to maximize its net profit. Possible approach: model the problem algebraically, model it in Excel, find its optimal solution with Solver, solve in graphics, ask a number of what-if to complete the model. Assembly and testing computers. Objective: to use LP to find the best mix of computer models that stays within the company's labor availability and maximize sales constraint. Solution: PC tech company must decide how many of each of the two basic models, basic and XP, to produce a maximum its net profit. The most it can sell are 600 basic units and 1200 XP. Each basic unit is 300, each XP is 450. The cost of the components parts for the basic are 150, the XB225. There's almost 10,000 assembly hours and 3,000 hours of testing available. Each basic requires 5 hours assembly and 1 hour for testing, and each XB2P requires 6 hours for assembly and 2 hours for testing. Each labor of assembly costs $5, $11, and testing $15. Here's a diagram of everything that's produced and how we need to go about determining which method we're going to use. Algebraic identifies the decision variable, number of computers produced, identify the decision variable, number of computers produced, and label these x1, x2. Write the expression for the total net profit and constraints in terms. Add explicit constraints to ensure that all x's are non-negative. The resulting algebraic model assembly and testing computers. Express the constraint and the objective in terms of x1 and x2. Graph the constraints to find the feasible region. Move the objectives through a feasible region unit until it is optimized. The graphical solution approach is not practical in most realistic optimizations where there's more than 2 decisions. Assembly and testing. Express the constraints and the objective in terms of x1, x2. I just did that. There we go. Spreadsheet model. There are 2 ways to develop an LP spreadsheet model. Common elements include inputs, all numerical values, that is, all numeric data given in the statement of the problem should appear somewhere in the spreadsheet. Decision variable. Cells, instead of using variable names such as X, use a set of designated cells for the decision variable. These values in these cells can change to optimize the objective. Additional common elements. Objective cell. One cell called the objective cell contains the value of the objective. Solver systematically varies the values in the decision variable cells to optimize the value of the objective cell. The cell must be linked to the decision variable by formulas. Constraints. Excel does not show the constraints directly on the spreadsheet. Instead, they are specified in the solver dialog. Non-negativity. Normally, the decision variables, that is, the values in the changing cells, must be non-negative. Change inappropriate. Overview of the solution. Model development stage. Enter all the input trials values for the decision variable cells and formulas relating these spreadsheets. The spreadsheet must include a formula that relates to the objective to the decision variable cells. It must also include formulas for the various constraints that are related to the decision. Invoking solving. Designated the objective cells, the decision variable cells, the constraint, and the selected options, and tells the cell the optimized solution. Sensitivity analysis. See how the optimal solution changes, if at all. Select the selected input. 2 variable product mix with an infeasible solution. 2 variable product mix with the optimal solution. Discussion of the solution. All of the inequality constraints, some are satisfied exactly and others are not. The XP maximum sales and assembly labor constraints are met exactly. Each of these is called a binding constraint. Binding constraints represent the bottleneck that keeps the objective from being improved. The basic maximum sales and labor constraints do not hold as equities. Each of these is called a non-binding constraint. The inequality is binding if the solution make it an equity, otherwise non-binding. Sensitivity analysis. In the real LP application, the solution to a single model is hardly ever the end of the analysis. It almost always useful to perform a sensitive analysis to see if the optimal solution changes as one or more inputs vary. 2 approaches to perform sensitivity analysis: the optional sensitivity report that solves offers. Solver sensitivity report performs 2 types of sensitivity analysis: one of the coefficients and the objectives of the right side of the constraint. The sensitivity report is requested in the solver final dialog box that appears on a new worksheet as shown below. The top section of the report is for sensitivity to change it in 2 coefficients and the decisions of variables. The bottom sections of the report is for sensitivity to change the right side of the labor restraint. Solver sensitivity report. To reduce the cost for any decision variable with a value 0 and the optimal solution indicated how much better the coefficient must be before the variables enter a positive level. The reduced cost for any decision variable is the upper bound. The optimal solution indicated how much worse its coefficient must be before it decreases from the upper bound. To reduce cost of the variable between 0 and its upper bound, the optimal solution is irrelevant. The term shadow price indicates the chance in the optimal value of the objective when the right side of the sum constraints change by 1 unit. A shadow price indicates how much the company would be willing to pay if the units of objective relax constraint. Solver table allows you to ask sensitivity questions about any of the input variables, not just coefficients, and the objectives to the right side of the constraint. 2A solver results for the 2 labor availabilities as shown. Comparison to solver sensitivity and solver table. Solver sensitivity focuses only on the coefficients of the objectives and the right side of constraints, provides useful information through its reduced cost, shadow prices, and allowable increase and decrease based on changing only the one objective coefficient side by side. Output can be difficult to understand if you lack the necessary background. Not available for the integer constraints, models, and interpretation of different. Solver table allows you to vary any inputs, provide some information, but requires a bit more work and experimentation and appropriate input ranges. It is much more flexible in this respect. Outputs are straightforward and can vary input and see directly how optimal changes. Outputs have the same interpretation for any optimal product. Proprietaries of linear models. Linear program is a subset of a larger class of models called programming models. All these models select the level of various activities that can be performed subject to the set of constraints to maximize or minimize an objective such as total profit and cost. In terms of the general setup, LP models possess 3 important properties that distinguish them from general mathematical programming models. Proportionally means that if the level of an activity is multiplied by the constant factor, the contribution of the activity to the objective and to any of the constraints in which the activity is involved is multiplied by the same factor. Activity implies that the sum of the contributions from the various activities in a particular constraint equal the total contribution of the constraint, also the value of the objective in the sum of the contributions from the various activities. Divisibility means that both integers and non-integers level of the activity are allowed. Discussion of linear properties. It is easy to recognize whether the models satisfy proportionally or additivity from the objective to be. This expression is called the linear combination of x's. Each constraint must be equivalent to a form where the left side is a linear combination of the right side constant. It is usually easier to recognize when a model is not linear when there are products or quotations, expressions involving decision variable cells. When there are nonlinear functions such as a square, square root, or logarithms that involve the decision variable cells. Real-life problems are almost never exactly linear, but linear approximations often yield very good results. Linear models and scaling. In a well-scaled model, all of the numbers are roughly the same magnitude. If the model is poorly scaled, then some large and some very small numbers, the round-off error is more likely to be an issue. There are 3 possible remedies for the poorly scaled models. Check the use of the auto-scaling option in the solver. Redefine the units in which the various quantities are defined. Change the precision settings in the solver option dialog box in a larger number. Infeasibility and unboundedness. A solution is feasible if it satisfies all constraints. However, it's possible there are no feasible solutions to the model. This is a mistake in the model. An input was entered incorrectly. The problem was so constrained that there's no solution left. Carefully checking and rethinking are required to remedy the problem infeasibility. Another problem in the unboundedness, the model has been formulated in such a way that the objective is unbounded. That is, it can be as large or as small as you like. If this occurs, you have the probable entered the wrong input, forgotten constraints. It's quite possible for the model to have no feasibility solution. There's no way for the realistic model can be unbounded. A large product mix. The problem we examine in this section is a direct extension of the product mix in the previous section. There are 2 modifications. The company makes 8 computer models, not just 2. Second, testing can be done on either of 2 lines, and these 2 lines have different characteristics. Objective: to use LP to find the mix of computer models to maximize total net profit and stay within the labor hour availability and maximum sales constraint. Solution: PC Tech now has 8 available models, not just 2, and there are now 2 lines for testing. The first line tends to test faster, but its labor costs are slightly higher, and each line has a certain number of hours available for testing. PC Tech must decide not only how many of each model to produce, but also how many to test on each line. So we have a diagram that shows all the constraints that we need to look at. And we can look at the 2 different product mixes and see how we can optimize it and make it feasible versus not feasible. You can also use the solver table to perform sensitivity analysis. The number of available assembly labor hours allowed to vary from 18 to 2,500 in increments of 1,000. The number of computers produced, profit designated as output. You can gain additional insight using the solver sensitivity, but we have to be careful of the interpretation. Multi-period production model. The distinguished feature of the multi-period production model is that it relates the decision made during several time periods. This type of problem occurs when a company must make a decision now that will have ramifications in the future. The company does not want to focus completely on the short run and forget about the long run. Objective: to use LP to find the production schedule that meets demand on time and minimum total production and inventory holding. Solution: Pinskin Company must decide how many footballs to produce each month. The company has decided to use 6-month planning. The pigskin has 5,000 footballs in inventory and forecasts monthly demands for the next 6 months: 10,000, 15, 30, 35,000, 25,000, and 10,000. Each month, the roughly capacity to produce up to 30,000 footballs. There's enough storage to store up to 10,000 footballs at the end of the month after demand has occurred. The forecast, the production costs per football in the next 6 months are $12, $12.55, $12.70, $12.80, $12.85, $12.95 respectively. The holding cost of the football is 5% per month. To simplify the model, all production occurs at the beginning of the month. All demand occurs after production so that all units produced in the month can be satisfied for that demand. The storage constraint and the holding costs are based on the ending inventory of the month. The spreadsheet model, pigskin production. Problem looks like this. The main features that distinguish this model from the product mix model is that some constraints are built into the spreadsheet model. The optimal solution is solved as shown below. Performance sensitivity analysis check to see, make sure it's there. Comparison algebraic and spreadsheet. For product mix, algebraic models are quite straightforward, and spreadsheet models are almost direct translation to Excel. For multi-period production models have two sets of variables, while spreadsheet has one. The algebraic model has multiple periods, must be related algebraically through a series of balanced equations. The extra level of abstraction makes algebraic models much more difficult for typical users to develop a comprehensive decision support system can help users solve problems without having to worry about the technical details of the LP. A spreadsheet-based DSS contains a spreadsheet model of a problem, but the users will probably never see this model. Instead, the user will have the front end, which allows the user's system's variables, and back end will produce the thing. Part of the optimal solution report is on the right. Thank you for Chapter 13.